Thanks for the introduction, Peter, and thanks again to everybody for coming along tonight. My name is Keelan Murphy. I work at the Infant Research Centre in UCC, and we're doing one of the research themes there is machine learning and deep learning using medical image and signal analysis. Thanks again to all our sponsors, and the first talk this evening is going to be a very brief introduction to machine learning for people who aren't familiar with it, and then we're going to go into deep learning, a sort of a high level overview, and then a little bit more theory of how it works under the cover. Okay, so just a sort of a high level introduction to machine learning. So the basic idea with machine learning is that you have this black box and you want to train the black box to do some task. So in this case, our task is going to be to distinguish image content from penguins, dogs and cats, photographs of these. So the first thing you're going to need is training data, and it has to be labelled. So you have to show the machine lots of examples for it to learn how to distinguish the image content. So you basically feed in as many of these examples with labels as you can, and the black box gets trained. And then at the end, you should be able to feed in an image with no label, and it should be able to spit out the label for you at the end once it's been trained. So you always have this training phase and then a testing phase. So the big question is what's inside the black box, and that can be lots and lots of things. So probably a lot of people here are familiar with various types of machine learning. So for the purposes of this evening, on the left I've got deep learning, which is basically neural networks, and on the right hand side is everything else, which is often referred to as conventional machine learning. So there's support vector machines, random forests, and so on and so forth. And a lot of these are very successful in lots of different areas and in Kaggle competitions and so on. But the one thing that they all have in common is that they use handcrafted features. So handcrafted features basically means that you, as a human, have to try and think of what features you would use to do this task yourself. So if it's image processing, you have to work out how you do that image processing task in your brain. And that's actually pretty difficult because we don't really know how the human visual cortex works and why our interpretation of images is as good as it is. So for example, if you have a task to distinguish images of houses from images of trees, you might try and think up some features. So let's say you first do some pre-processing and remove colours and just detect the edges in your image. You might decide that some good features for distinguishing houses and trees would be texture and curvature. So the house doesn't have much texture in the image, and the tree has a lot of texture, and the lines of the house are mainly straight, whereas the lines of the tree are mainly have a lot of curvature. And if you've picked out good features, then you should be able to divide your samples in feature space very well. And in this case, it looks really nice. We're able to divide them linearly, and we should be able to do predictions based on that. Of course, that's very simplistic, and in practice, anybody who's done machine learning before knows that what you come up against are counterexamples like these ones. So you have a tree that doesn't have much texture, or that doesn't have curvy lines, and you have a house that has lots of curvy lines and lots of texture. And then you're back to the drawing board and you're trying to think up new features, and how is it that I still know this is a tree and I still know this is a house. So deep learning basically consists of neural networks, which, well, depending what age you are, you probably learned about them in university for a long time going back. And the only thing that makes them different than the neural networks we all learned about 20 years ago is that they have lots of hidden layers. So on the left, this is always known as the input layer. On the right, we have the output layer, and everything in the middle are hidden layers. And lots can mean anything from 2, 3, 4. Nobody has actually defined what defines a network to be deep. As long as it has more than one hidden layer, you could actually call it deep. And the nice thing about these is that the network determines what features are useful. So you don't have to do any of this handcrafting of features. You just throw in all the labeled data. This is a cat, this is a penguin, this is a dog. And the network should figure out for you what the features of those things are that make them distinct from each other. This is just a little graph to show why you might like to use deep learning. And the literature from the past decade bears this out, that if you have a lot of data, you will almost inevitably get a better result using deep learning than you will with older learning algorithms or the conventional handcrafted feature algorithms. If you have a small amount of labeled data, and that's true in lots of domains, you may well do better with a different algorithm, because deep learning is very data hungry. But again, that's starting to change a bit, and there are ways to make deep learning work with smaller amounts of data all the time. Okay, so I'm just going to give a sort of a very high level overview of how a neural network works first, and then we'll kind of delve into it a bit more. So as I said, on the left you always have your input layer. So let's suppose that our input is images of cats in this case, and dogs and penguins. So you feed in some training data. So this is a training image of a cat, and we're going to feed it through the network from left to right. These blue things are called neurons or perceptrons, and they're just, you can think of them as just arrays of weights, and you're going to do something with those weights and something with the numbers that are belonging to the image. So the image to the computer is just a big pile of numbers, right? And as it goes through the network, the data eventually comes out at the other side, and you have an output layer with 3 categories. And what should come out are 3 probabilities. Probability that this is a dog, a cat, or a penguin. Now you can see that the network at this point would be doing pretty badly because the probabilities for all 3 are almost the same. But luckily when you're in the training phase you have the labels, and you can use those to your advantage to train the black box to do stuff better for you. So in this case we know that the probability for cat should be 1 and for dog and penguin should be 0. So we're able to calculate our error in some way, and there's lots of different functions to do that. And then you do something called back propagation. And that means that you basically use these error values, you go back to your weights, all of these arrays of weights in the neurons, and you change those weights, each one a little tiny bit, to try and make your error in that case smaller. And then you do this with lots and lots of training images, so as many labelled images as you can get your hands on. And each time you put a new image through, you update your weights another tiny bit, and you're getting incrementally closer and closer to the right solution for the optimal solution for your weights. So when you're finished training and you've put through as many examples as you can, you come to the testing phase. And as I said before, this is where you feed in the data with no labels. And you test the network to see how it does. And if you've optimized your weights correctly, you should get some output that looks a bit like this. So penguin should have a very high probability in this case, and dog and cat a very low probability. Okay, so let's delve a bit deeper to look inside the neural network. So this is a really sort of basic example. So instead of an image on the left now, I'm just showing a very small array. So it's just a one-dimensional array, 4 values, x1 to x4. And here we have just one hidden layer with 2 neurons in it. And each of the hidden layers has 4 weights. And it's set to have 4 weights because we have 4 inputs. So that's how you define your number of weights. You have to have 1 for each input. And you also have something called a bias term, which I didn't mention before, but it's just an additive term that we put on the end. And what comes out when you pass your input data through those 2 neurons is here on the right in the green boxes. So you just have each weight multiplied by each input, all summed together, and at the end you add the bias. And then that gets pushed through into the next layer. So if you look at those green boxes, they might look a bit complicated, but actually we normally write this all in matrix notation, which makes it a lot simpler. So then you have x is a 4 by 1 array, W1 is 1 by 4, B1 is just a number, W2 is 1 by 4, B2 is just a number, and when you push them through you have W1 x plus B1 is your output from this neuron, and W2 x plus B2 is your output from this neuron. And actually in the code, when you normally write this in code, you do it even more simply still, because you combine all your neurons into one stack. So you actually have a 2 by 4 matrix of weights and a 2 by 1 matrix of biases, and out of that comes a 2 by 1 output. Okay, so that's just the notation that we use, and when you're looking at the code, the TensorFlow code, you'll see these matrices, and it's good to kind of bear in mind what sizes the matrices should be, because those are the kind of things that trip you up along the way. Okay. So far we've talked about the output from the neural net, or from the neurons in this layer, being Wx plus b, and most of you probably recognize that as a linear term. And it turns out if you push a linear term through to the next layer, and then from that layer you push another linear term, and then you push another linear term, it turns out that in the end your input x will have a linear relationship with your output y. So obviously that means you're not able to model any very complex relationship, you're only able to model something that's linearly related. So instead of having this whole linear relationship, we need to put in some non-linearities, and that's where the activation function comes in. So the activation function here is called g. We apply it after each layer to Wx plus b, and it can be, well, it could be potentially any function, but only certain functions will work well. So for a long time the sigmoid function was used as the activation function, and it's no longer recommended for a few reasons. What's normally recommended now, especially as a starter activation function, is the ReLU, which is the rectified linear unit, and it looks like this. So it's a really simple nonlinear function. It's basically 0 if your input is below 0, and just the same as the input after that. And it's very quick to compute, which makes it ideal for our purposes, and it works very well. Okay, so far so good. We're feeding in our input. After each layer we're pushing through g of Wx plus b, and we want to get to our output layer, which is dog, cat and penguin. Now I said that this output layer would spit out probabilities of which would sum up to 1, presumably. That's not actually exactly the case, because what it actually spits out is some numbers, which are often referred to as logits, and these numbers don't necessarily sum up to 1 in a nice probabilistic fashion. And so we add in a function called softmax, and all you really need to know about the softmax function is that it turns this pile of numbers into a pile of probabilities. So the bigger numbers get mapped to higher probabilities, essentially. There is a formula for softmax for anybody who's that way inclined, but again, you don't need to know this technically speaking. It's all pre-programmed for you in TensorFlow, but it's just good to know that that's what the softmax function is doing. Okay, so again, so far so good. We have our softmax and we have our output, and now we need to look at backpropagation. So again, we're going to compare, during our training phase, we're going to compare our output with our training labels, and we're going to calculate this error function, and we're going to do this backpropagation where we go back and update the weights. A lot of people think this is the really complicated part of deep learning algorithms, and in a way it is, but it's actually not all that difficult either. The mathematics of it is relatively simple. I'm not going to go into it tonight. I'm going to give a kind of a high level intuition of how it works, but the mathematics of it is actually not that complicated either. And also, you never have to implement this. It's all implemented in TensorFlow or whatever other package you choose to use. Okay, so just to remind ourselves, error, this little error red arrow that I've been mentioning, is measured by something that is usually called the loss or the cost function. And that's a function of the network outputs, obviously, because the labels are fixed, so it's based entirely on what comes out of the network. And the network outputs, obviously, are functions of W and B, the weights and the biases. And if we recall, we want to update the weights and, in fact, the biases to reduce the loss. So if you imagine the loss as a very simple function like this, and this is just a function of just one single weight, W1, what we want to do, if we start over here and W1 has a value of about 4, we want to find which direction we need to move W1 to get lower down in our loss function. So we want to find this direction, and that's essentially just finding the slope of this curve. And so the method to go down to the bottom is called gradient descent, and it works like this. At each step you do W1 is equal to W1 minus alpha times the differentiation of the loss function with respect to the weight. And alpha is the learning rate, or the step size, so it determines how large a step you're going to take in that direction. And that this differentiation term is just the slope of the function in this case. You can imagine that in a one dimension higher, where we have two weights, W1 and W2, and our loss function now looks like a surface. And if you're at this point on the surface, you want to take a step in the downwards direction. A lot of people get caught up with the idea of local minima, that if you go down here, you're going to end up in this minimum, where you really want to be at this minimum. And it turns out that in a very high dimensional space, and bear in mind that these networks often have tens of thousands of weights, in very high dimensional space, that doesn't turn out to be a problem for us. Okay, so in TensorFlow and most other packages, we call the optimizer the thing that we decide the thing that decides how we should move to reduce loss. So gradient descent is the most basic type of optimizer, and there are lots of other kinds of ones that people have developed, and these are some of the names: Adam, Momentum, or MESPROP. They're all based on gradient descent, but just with some extra smart bits added on to make to make your descent a little bit more efficient. Okay, so this is the last slide, I think. So I'm going to just talk about the TensorFlow tutorial, the very first tutorial that we're going to implement. So we're going to use something called the MNIST dataset, which is a kind of a benchmark dataset for lots of machine learning and deep learning algorithms. It's a set of handwritten digits, and each of them is encoded as a 28 by 28 image. So this is an image of a handwritten 5, and it's 28 by 28 pixels, and they're all the same. They're actually stored already flattened in this one-dimensional array, which is good because these networks that we're looking at the moment can only handle one-dimensional arrays. What we're going to do is we're going to feed them into the network in a batch. So that's something I haven't mentioned yet, is that you don't usually feed your training data in one sample at a time. You normally feed it in a batch. There's a few reasons for that. I guess it's more efficient. You don't have to go back and update your weights every time you've just seen one new image. You want to actually see a batch of them. You average your error over that batch, and then you go back and update your weights. We don't actually have any hidden layers in this network that we're going to implement, the very first one. So we just have one output layer. And the output layer has 10 neurons in it because we have 10 classes that we want to classify our data into. So the digits 0 up to 9 are the 10 classes. So from those 10 output neurons, obviously we're going to have Wx plus b, we're going to apply our softmax function, and we're going to get some probabilistic output. So again, our probabilistic output is going to be a stack of 100 things because we fed in 100 samples, and each of them will have an array size of 10. And you can imagine one probabilistic sample looks something like this. So these are the probabilities for all the various different classes. And we're going to compare those with our truth samples. And again, our truth samples are encoded like this. This is called one-hot encoding. So it basically means that the element that is 1 is the element that the true class is. So in this case, it's a 3. So it's the 0, 1, 2, 3 the third element that is classed as 1. And we're going to then use an error function called cross entropy, which you can look into yourselves, but it's a very commonly used error loss function in deep learning. Okay, so Peter's going to talk a bit about TensorFlow next, just to give you an introduction to the language and why you'd want to use it. And then hopefully if the Wi-Fi is set, we'll be able to work ahead with the next tutorial.